So here we've got an exponential function, and it's going to be exponential decay because there's a minus in the k, and it says that k is positive. So it does actually help, I think, if you have an understanding of what this graph's going to look like. So it's going to start somewhere along the x-axis, and then we're going to get exponential decay. And normally, if we just have e to the minus kt, then it will go to 0. But here I've always got this 25 going on. But this is like a typical kind of curve for temperature reduction, actually. So this actually answers part 1 and part 2 pretty much. So write down the value of a. Well, that's when t is 0, little t is 0, capital T is 100. So I can just substitute these in, and I'm going to get that 100 equals 25 plus a e to the 0. E to the 0 is just 1, and so I can see I'm going to get a equal to 75. Explain what the value of 25 represents. So as t tends to infinity, what's going to happen? This thing here, this second term, is going to get smaller and smaller. However, the 25 is always going to be there. So t is going to tend to 25. And that's actually what's going. So this is 100, and this is actually my 25 here. So what is the 25? 25 is the temperature of the surroundings. Temperature of the surroundings. Sorry, I'm trying to squeeze this in. I should have written it below. Sometimes referred to as room temperature, but we don't know if we're in a room or where we are. Sometimes also called the ambient temperature. When the heat switched off, the initial rate of decrease is 15 degrees C per minute. Right, rate of decrease. That wants us to work out what dt by dt is. So I have that d capital T by dt is going to equal, now let's update this equation. We've got 25 plus 75, whoops, e to the minus kt. So when I differentiate, I'm going to get minus 75k e to the minus kt. That's my general rate of decrease. So I know the initial rate of decrease is 15 degrees Celsius. So a decrease means it's going to be negative. So I can write down that minus 15 equals minus 75k e to the 0 again. This just is 1, so I can ignore it. So then I'm going to get that k is a fifth, or 0.2. I think I'm going to write it as a decimal here. So I can now update my equation again, and I've got that t is 25 plus 75 e to the minus 0.2 t. Find the time. Actually, I'm going to bring this down here. Right, part 4. Find the time taken for the temperature of the water to drop from 100 degrees to 45 degrees. So we know it's 100 at the start when t equals 0. I want to find the time at which it's 45 degrees. So I can set t equal to 45, and the only unknown then is little t. If I minus 25, I get 20. If I then divide by 75, I'm going to get 20 divided by 75 is equal to e to the minus 0.2 t. And now I can use my knowledge of logs. There's two sort of ways to do it. I'd probably say learn both sides. Okay, if we're being careful, and then I can bring the minus 0.2 t down. and then ln E is just equal to 1, so I can just ignore that. So I've got this. You can go straight from here to here if if you have this appreciation that that's what a log is. It's the power here. It's going to be e to the power of minus 0.2t is 20 over 75, and it works the same kind of way if we've got ln. If I've got this equation here, then it must be that ln of the thing on the left equals the thing as the power. But in any case, as long as you can get to this, that's the main thing. So then we can work out what the left-hand side is, and we can divide by minus 0.2. We get that t is 6.6087, which is 6.61 minutes. Finally, a second pan's heated, but the heat's turned off when the water is at a temperature of less than 100 degrees. How can we modify the equation? Well, let's just think about this. K gave us how quickly it was decreasing, but it's going to be sort of decreasing at the same sort of rates for a given temperature in any case. So it's just that we're going to maybe start here instead, but it's then still going to decrease at the same rate. So we don't want to change K. The thing we want to change is A, because A told us the starting temperature. 75 added to 25 gave us 100. So what do we need to do to start out a temperature less than 100? We just need to decrease A. So this question's nice because it's a bit of solving of exponential equations, quite a lot of understanding of mathematical modelling of these sorts of things. But yeah, quite a few marks. We've got 9 marks here, but little questions here and there as well.